I think the stream's up. Hello everyone. Just getting the kind of file ready. We will be going over lab 5 today. Hopefully a quick one. But again, ask any questions as they come up. Code-wise, there's not that much going on here. But I'll give it a few minutes for people to connect. And again, kind of the idea with this lab was the OLI module and recursion. Kind of covered both of these two in terms of like pseudocode and thinking about them, and kind of doing that like logic walkthrough of it, but it didn't really have the explicit code for it. So I thought it'd be really nice to actually have us do the code for it. And another popular thing that people do with recursion is kind of compared to the iterative solution option. And these are two pretty common ones, factorials and the GCD. So also if you kind of Google like recursion and then GCD or recursion factorial or like Python recursion even, it's likely you can find these. But I still think they're really good examples. I mean, there's a reason they're so popular, right? So hopefully you were able to kind of do them prior to searching, or maybe if you did run into trouble with either of the two, hopefully referring back to the OLI module or kind of doing some searching led you to a kind of walkthrough or something, or just seeing the tiny bit of code, and hopefully it all kind of clicked for you. Recursion is definitely a difficult concept, especially when you kind of start using, like for GCD, if you start using larger numbers, or maybe if you're kind of coding it for the first time, sometimes it's not the most intuitive to like swap these variables around, or to even initially use like modulo. So it's definitely not the easiest thing. Also kind of like where and when to return and what to return, I know is kind of a problem sometimes. But hopefully things are kind of cleared up by now. If not, hopefully when we kind of work through the code, it will be. And I think probably if you're still running into trouble, maybe the best thing you could do is to use that visualization tool we kind of walked through last time. The like Python tutor. If you just search for that, it should be this first one. Then you click Python tutor. So I guess technically this is the URL. And once we kind of go through the 4 kind of functions, I'll go ahead and throw one of the cursive ones in here and demonstrate it, kind of looping over. And I think that might help probably more than any kind of words that I could say to explain what's going on, because you can really trace the variables it's going through. So hopefully that'll help to clarify anything. So we'll go ahead and throw the recursive ones for factorial and GCD in here once we kind of go through them in the code, which shouldn't take too long because they're not that lengthy. But I'm going to go ahead and dive into them. So let's read the instructions. The first 2 functions, let me pull up this, make sure my mic is going. Looks like it is. The first 2 functions in the provided file are factorial recursive and factorial iterative. Each of these should accomplish the same thing, which is returning the factorial of a number. And again, here's like a little Wikipedia link if you hadn't heard of the number factorial. The first function, recursive, should do it recursively, so it should call itself, which hopefully you kind of knew that was going to be the case when you saw the word recursive after doing the module. And then the other one is kind of iterative solution, so it should use like a for a while and not have to call itself. And then we do the same thing for this greatest common divisor. Again, there's the link provided in case you were not clear on the topic, but I'm pretty sure OLI covers both of these in terms of idea. So I went ahead and threw the starter code in here, and we can just dive in. So another thing, so if I'm going to do like factorial, start with an easy number, let's do 5 factorial. There's some videos on it, I'm not really sure what that is. But that is 120 is 5 factorial. You could go to one of these and kind of see the work through of it. And we could even do it in here, right? So 5 times 4 times 3 times 2 times 1, we get 120. So, maybe I'll use that as kind of my starting case. So with a factorial too, if it's, we're gonna wanna maybe start from this back here, and so if it's 1, we're gonna wanna go ahead and kind of return 1. So it's also not gonna get less. So if we just do num less than 2, and again, the more of this like logic and breakdown should be no li. But you always kind of want like this base case kind of thing, like something to stop this recursiveness, right? So you always need a return, and you're gonna need a return statement that gets hit when you're doing recursion. So our case is going to be if num's less than 2, so then as I feed in num to this function, we're going to want to somehow decrement it, right? Decrease it. And it looks like OLI was loaded for me. It's been a little slow, honestly. I don't really want to read on these pages. I totally forgot if it's on here. Let's see. Yeah, I think it's going to be slow for me again. Oh well, but I think we kind of, oh, okay, here we go. So yeah, going over GCD is nice. Let's go to the next page, we keep this one up. Yeah, then here we go for factorial, right? So there's like 1, if n's equal to 0, then display 1 as a result, otherwise continue the next step. So now we're kind of breaking this down, right? This is what I try to do for the homeworks. Sometimes, in the office hours, I'll kind of break it down line by line. So we're basically implementing this kind of stuff to code, right? And so, as we talked about, we kind of have this base case where we're going to want to return something. And so, in our example, it's going to be num. And so, for num to actually trigger this if, it's going to have to be less than 2. So, 1 or 0 at one point. And that means we're going to have to somehow decrease the value of num, and this kind of gives it to you right here, right? Factorial n minus 1. Because the actual kind of like meat of the function is going to be, so else, if we actually have like a 4 or a 5, we start with 5, right? So let's say start with 5. We don't want it to go ahead and return 1. But what we're going to want to return is like 5 times, and then eventually it's going to want to be like 4. So we have our else. I have this return that was there by default, which is fine, actually. So we're going to return, for input 5, you want, here we go, to return 5 at one point, so that's what we're doing here. And then we're going to want to multiply it by, and this is where we get all recursive on it. Oop, didn't type it right. Actually, still don't trust my typing, so let's copy this. Num minus 1. And that should be it. Because, then num minus 1 is going to return 4. And so we feed 4 back in here, and then this becomes the return 4. This becomes 3. Then pass 3 in here. This becomes 3, 2, then 2 again. Then we pass in 1 here, and then it hits our case, return 1. And so we can actually test this as well, and we will walk through this in the visualizer in case you're still unclear. So passes that case. Let's do a bigger one, 10, and we'll do 10 total, which is this large number, 3.6 mil. And we did get that. So basically what we're doing in that case is walking through this kind of logic that's described here in this page, and you got to kind of play through with recursive and base cases, and translating it to code. Make sure there's no questions. And again, I'll throw that in here. Actually, we'll go ahead and copy it in here. But we won't walk through it yet. I want to do the iterative case. Actually, I want to do GCD as well, and then kind of walk through these in case they're needed. Can't type today. Factorial, recursive. Okay. So we'll just keep that. Go ahead and open up another one of these for our GCD once we get there. But alright, so we have that code. And now we want to do the iterative solution for it, right? So for a while loop, in this case for factorial, I'm going to use a for loop. I'm sure you can solve it with a while loop, but I guess the way that always comes to my mind first is going to be with a for. As with kind of most loops, honestly. So let's start with kind of a case where n equals 1. And we're taking this input num that we're gonna want to kind of like go up to since we're doing iterative solution. So like, we know we're gonna want to start kind of almost backwards if we're gonna do this loop, right? Because we can iterate from like 1 and you keep incrementing this number up to 2, up to 3, up to 4, up to whatever the final number is we input. So if I start with 1 and basically do something with this n all the way up to the number that we input, it kind of lends itself to doing like a for loop, right? And we're going up. So I'm going to want to have this variable n equals 1 first. And then I'm going to want to do I, and range. And so again, if you open up this, you can see the stop. If I just put in one number, or the start and stop, and then the step, which we won't be using step, but we will want to start at something that's not just 1. We're going to want to start at 2. Kind of similar to this base case here, right? It's 2. And then we don't want to just go up to the number because we're going to want to include it, right? So if you do 5 factorial, it does make use of this 5. So we're going to want to do num plus 1, right? And then we'll do times I. So we kind of loop. We can even actually print these. That might help too, as opposed to visualizing this one. Number in for loop. I. Right. And then we'll have to use that num. And yeah, so that should just be it for this iterative solution. Let's check. Pretty sure I'm not forgetting anything on there. Yeah. So then you can see, it starts at 2 for the first time and it works its way up. We're just doing the kind of basic for loop, and then since it's in range and we start at 2 and we have num plus 1, it includes 2, 3, 4, 5, and we already have it at 1. So, it's doing like n equals 1 times 2, and then n becomes 2, and then we do n equals 2 times 3, and it keeps going, and then it becomes 2 times 4, and then 4 times 5. And so it basically does like all of these like in one loop, or actually it would go from this way. So then we get 1 times 2, do that 2 times 3, 3 times 4, 4 times 5. And just does it kind of like in those 2 segment chunks per, and you can kind of see that by the what we print out. And yeah, I guess we'll also test it with the 10, but that's the iterative solution for factorial. And again, it's equal to the large number. Make sure there's no chat. Yeah, so that's it for factorial. I think, common problems are maybe like keeping in the range as 1, or not adding this 1 to the num for the iterative solution. And again, for I think for actually a lot of recursion problems, even when you solve them iteratively for this, there could be confusion on what to pass back in. Like, do we decrement it by 1? Do we just pass it back in again? And also kind of having like the base case of when to stop is often challenging as well. But hopefully kind of OLI breaking down the high level logic helps clarify that. Or kind of troubleshooting with it, like adding print statements to make sure you're getting the variables you expect. But I think with GCD recursion in particular, it's maybe not the most intuitive on the passing of the variables in there, which we will cover right now. And then visualize. So, right here, the last 2 functions are GCD recursive and GCD iterative. These both return the greatest common divisor of the 2 inputs, which we walked through in the OLI module. Again, recursion function should call itself, and the other one should not. And then here we go with kind of the logic, right? And there's examples here. So like the largest number that can go into both 18 and 42 is 6, right? Because it can go into 42 7 times, go into 18 3 times. And then here's the recursive solution, again with these kind of assumptions. X is greater than 0, y is greater than 0. We do make use of that modulo function. And what's kind of nice too about this is it gives you the, I think this is probably the most challenging part, for me at least it was. But again, everyone varies, but the kind of like, so we take in this x, y, it's kind of weird. But yeah, so we take in the x, y, and it actually kind of tells you what to compute here. X modulo y is equal to 0, display the result. Otherwise, you know, let's get the recursion going, but you have to swap them, right? So then you do pass in the y first, and then you actually input for the y, this x modulo y value, and then they become your new kind of xy. And so, you know, this kind of gets into the logic more, but basically we're translating this part to code. So, I like starting with the kind of base case first. So, I mean, you are also welcome to change these to x, y if you want to kind of make them more reflective of the OLI code. Then it's super translatey to it, but so if this like x modulo y is equal to 0, and we know we kind of get x modulo y here passed in as the second variable, which for us is num2. So we can go num2 is equal to 0. Also, well, visualizing will help. We'll talk about why we're also returning like num1 as opposed to 1. And then kind of similar to factorial recursion, we just throw in the else, and then we make our kind of recursive call here. But since we're not like kind of adding something as we go up, so with factorial, you know, we input this number and we have to do like all the sub numbers of it, like 5, 4, 3, 2, 1. So we kind of have to keep this like running term in a way. So we had this separate thing like num here in addition to the call. But since we're just looking at like this number that can make up both these two numbers, we don't really need to keep track of that, since our kind of second input is the thing that gets like decremented per se. Not, in this case, it's not always necessarily decremented, but something that becomes reduced, right? Because with recursion, you can get in this kind of infinite loop. So you're always going to want to like input something that is altered, and generally something getting less, right? So, or greater, I guess, too. But, you know, you're going to want the numbers to change. We wouldn't want to just swap, like, y and x in here. And then the next time we call it, then it just goes back to xy, and then we call it again, it goes yx. Because it would just keep going, right? So you need something to be changing. So that's also kind of a thinking strategy, too, on, like, hey, what's going to change that makes, like, our base case eventually get hit. And, you know, kind of as we can see here, we're gonna swap these inputs. 1 modulo, 2, and that should be it. So, you know, we get this, whoop, need a double equals here. I was doing assignment rather than equivalence. And so we can just do the case, what's it called, recursive, right, of 42 and 18. Get 6. And that should work as well, right? And yeah, that's the recursion one. So let's go ahead and throw this in here to get a nice visualize of it. Let's call it GCD recursive, and we'll do the same case of 42 and 18. And I'll do the iterative example real fast, and then we'll walk through the visualizing of it. Make sure there's no questions. I actually think for GCD2, the iterative, I don't know, maybe I'm just not used to working with GCDs, but I find both of these harder than either the iterative or recursive solution. Like, I find the factorial recursive personally easier than GCD, even iterative. But that's maybe just my thinking, right? So we're gonna need like write a for a while loop here. And in this case, are we doing a while loop? And again, I'm sure you probably did with a for, but the just natural way that I'm thinking of GCD is we're going to want a while, because as we kind of decrease this number, we want to like keep doing this kind of modulo and number swap while our input, which is going to be the second one, is greater than 0. So, you know, it's kind of like this, but instead of the else where we continually run it, we're going to want to kind of almost morph this into like a while, if that makes any sense. Maybe I'm just causing more confusion as I try to articulate my thinking. So all this, and now we're just going to want to do like the kind of body of it, the whole swap thing here, right? So we're going to want to like keep track of number 1, so we'll do old number 1. And then we're going to want to do number 1 is number 2. So we're swapping out these kind of variables. And then number 2 is going to be this old number 1. Modulo. We find it. Number 2. And we're going to eventually just want to return whatever number 1 gets hit at. Yeah, pretty sure. So, you know, it gets to this, and then num2 becomes a new value, and so we go back to the start, and we check this new value of num2, and then we go through, but we're doing kind of the same thing here, right? Very similar. But let's test it. Alright. Good. Alright, let's walk through now some visualizers, which I think kind of help clear things up. So we'll just jump to recursive again, right? I think I typed the numbers in right. Okay, we did. Then hit forward. This just basically says, hey, we have this function, but now we're calling it, so now we're going to actually dive in and kind of do the tracing, right? So we input, this number is 5. Our number is less than 2, no it is not, so we don't hit that. So we go to the else, and then we make a return of num and the factorial. So this kind of repeats, 3, 2, and 1. So, you know, it is num less than 2. It is. Let's return that 1. So this is a return value is now 2 from that. This one's getting hit now. And it's kind of, so you'll see that they wrap up. Sorry, return 1. And then it kind of, you know, it makes these chains. And then we finally hit this return 1. So we stop the kind of recursion. We were only calling this function 5 times in a row. And now it's going to wrap back up here. And here, and here, and here, with our returns from right here. So you'll see that as we go along. So it's boom, 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 boom. Right? So we have like, you know, 2 times 3, it's going to get 6. 6 times 4, it's going to be 24. 24 times 5 is going to be 120, and so we're returning 120, and that's it. So hopefully that kind of shows the wrap up. I think the kind of confusing part is like how many times this factorial recursion gets called, and so we can see all the calls to it right here. But this one hits the return 1, so then it doesn't make any more calls. So then we can finally like finish or wrap up in a way these calls, right? Because we were diving into these more calls here through this return statement of like this part. And so now that we finally got 1 from it, I don't know what clicking that does, but then we can kind of like, okay, now let's finish this num and multiply by that and do these return statements. And so that's what that's kind of doing. So hopefully that helps some. I mean, definitely play with this with different numbers and all. But I think it's nice to see how many times we're actually calling this function, and then finally knowing when this return gets hit, then we can focus on these returns from the previous calls, and then watching that value and return value go up, right? But Again, if you can just like kind of grasp these two examples, I wouldn't worry too much about other ones. Because just like kind of thinking this way and being aware of it, I think is the more important part. But as you can see, even when there are recursive answers, you can do them iteratively as well. I want to say in every case. Don't quote me on that though, but I'm pretty sure if it can be solved for recursion, it can be solved iteratively as well. Especially in like a realistic scenario of where you might want to have one of these functions, right? So, and then let's do the GCD recursion one. I apologize if you can hear these birds outside my window. All right, yeah, so it's just saying, hey, we have this function here. Now let's actually make the call. So these are inputs, right? 42 for num1, 18 for num2. Hey, is num2, which in this case is equal to 18, is that equal 0? No, it is not. All right, well, let's do this GCD recursive call. So we call it again, but again, we're swapping these inputs. And for the second one, we're now doing modulos. So we are doing 42 mod 18, which we got 6. And we continue. So again, num2 is not 0. Make the call again. So in that case, we pass in 18 and 6. So then we're doing 18 mod 6, which goes into it smoothly, right? And then we swap the numbers again. And so by knowing it goes into it with no kind of leftover from the modulo, we know that it's like a perfect divisor, right? Because 6 can go into 18 3 times. So 6 is good, and we've narrowed it down that it can also go into 14. So then when we pass in this num2 of being 0 right here, and then 6 here, so then 6 becomes num1. And by the 0 of num2 equals 0, it's telling us, yeah, whatever the value of num1 is like the divisor, the largest divisor, right, the GCD, that goes into both these numbers equally. So then, yeah, we do have num2 0, and so we can just return this num1. And it wraps it up, right? We're not like incrementing a certain value or anything like we were for the other ones of like keeping this running tally of n that's getting bigger and bigger. We're just, returning the value of here. And so that's only going to get hit when num2 is 0. All the other ones were just returning this recursive call. And so they all return that one initial value. So that's why our step of return value 6 stays the same. Poop, poop, poop. Yeah. So from what I saw the labs, everyone seemed to do good, and there were some different solutions. Again, I'm sure there's like, if you're still kind of stuck, Python GCD recursion. I don't know any of these websites per se, but why not Stack Overflow? But you can find different kind of samples of the code, but this is like what we did, just different variables, and kind of explains it. Stack Overflow might not be the best for this kind of stuff. They get a little low level, but hopefully the visualizations and me kind of talking through it a little bit, and this kind of logic breakdown helps to clarify anything. But if not, definitely post on Piazza, shoot me an email, preferably Piazza though, and we can maybe see what part is giving you trouble in particular. And again, if I'm grading the labs and I see that maybe you don't have a complete solution for one of them, or left me a comment, I can hope to provide any clarification there. But yeah, if you kind of grasp these two, definitely congrats. Recursion is a difficult concept, particularly for the kind of early CS stuff, that I think is sometimes overhyped and how much it actually comes up, but I do think it's super useful to know. So that's why we included it, and kind of gave these two little examples. But no pressure to use it. And the fun Google Easter egg is if you search for recursion, this is usually the thing you typo, right? So if I like reverse it, but for recursion, it just always has it there, right? Because it's like the kind of infinite recursive loop. So that's a little Google kind of nerdy Easter egg that you can go tell your friends about. They don't know. I think it's kind of funny. And I actually forgot about it and ran into it when I was actually Googling recursion to kind of make this lab. So, fun Easter egg that you're now aware of if you weren't, for a topic that's generally pretty challenging. So, hope you get that. There's one more module we have, one more week of class. No quiz for this week, as I announced. No quiz next week either. I originally didn't even have the kind of final quizzes in the grading structure anyway. That's why they weren't an LI. But then at the last minute, I was like, oh, maybe I can throw in some quiz stuff for them actually. Then these conferences kind of tied my hands and I got too busy. But I'll still kind of release some beneficial materials that I think will help for PUI, but we won't so much use in this course, which is fine. And yeah, looking forward to the last homework. It'll kind of be a summation of all we've learned in addition to a little new thing, also geared toward helping you with PUI. And so while there won't be a quiz next week, I think looking over this one kind of resource that I'm going to link for like 15 minutes will be beneficial. But hopefully if you like this homework this week, I think you'll like the next homework. Yeah, and I'll stay on a little more for a couple minutes for questions if any pop up, but probably not too much longer. But again, on Piazza, I'm caught up to date in all of these questions. Homework due Monday at the usual time. No quiz due tomorrow. Yeah, lab was due at noon. And I think that's everything. For us, I'll be on a better computer with a mic and 2 screens Saturday, so we can kind of go into any of the homework in more depth if needed. It'll be a little better quality. Won't be on this kind of terrible laptop setup. But next Tuesday and Thursday I will be back on the laptop. And I got to work on some of the grading a little more today. And hopefully I'm going to be able to take another big chunk out of it tomorrow and try to get those out. But again, if anything was glaring on the stuff I've graded so far, you would have got a comment or an email by now. So don't fret on that front. All right, I think I'm going to sign off. I'll keep an eye on Piazza. Hope everyone has a great week and enjoys the 4th of July. If you partake in July 4th stuff, I'm sorry that we had a lab due on this, but there's a tight timeline for this course that I did not set. So I'd like to defer any blame there. But hopefully the lab and homework and not having a quiz kind of gives you a little more time than maybe you would think. But yeah, hope everyone has fun and safe travels. I know a lot of people are traveling, so yep, I will see some of y'all Sunday then.